Okay, we have ourselves a Kinematics Freefall A plus Physics Solutions video. Here's the worksheet. Page 1, 1 through 8. Page 2, 9 through 9. Stop that. 9 through 20. Page 3, 21 through 27. Stop that. Alright, and we are good. So let's begin at the beginning with number 1. Now actually 1 through 4 doesn't have a lot to do with free fall. It is about an object falling. But if you actually walk through everything that you need to do, none of it, you don't need to know free fall physics to solve. It's really just working with a plot. I'll write up the solutions anyway, but I'm going to write it up and then move on to number 5. You'll see at the end of this solution that you actually don't need to know any free fall physics to solve questions 1 through 4. Why did they open up the worksheet about free fall kinematics with 4 questions that you don't actually need to know free fall kinematics? I don't know. I didn't make the worksheet. No one asked me. To be fair, it is a Regents question, and it does have to do with an object falling, so if you're going to stick it anywhere, I guess you would stick it in free fall kinematics. Alright, enough of me running my mouth. Let's see what the solution is. So the first question says, mark an appropriate scale. So we have to scale the graph axis. And we start with 0, and then we have 1, 2, 3, 4, 5 levels to choose from. The way data tables are constructed, you can see our data table on the page. We have height, then speed. Data tables are always x column first, then y column, x comma y. We can see that speed is already on the y-axis, so we have to scale the height. But these numbers are already well set up for scaling. They're already evenly spaced. 5, 10, 15, 20, 25. To be clear though, the way we scale a graph axis, we don't just take the numbers in the data table and put that as the major axes on my graph. Look at the speed graph. Notice that the speed values in the y column are 9.9, 14, 17.1, 19.8, and 22.1. But that's not what they put as the major axes for the speed, for the y-axis, for the speed axis. This is 0, 5, 10, 15, 20, 25. Because the way you scale a graph axis, you have to scale it by even amounts. Evenly spaced amounts, I should say. It actually goes by 5s, that's not an even number. But by even, I mean like evenly spaced. Alright, number 2 needs a plot. So we're just doing x comma y, and we're plotting the height as a function of the speed. So we're starting with a speed of 0, and the height would be 25. Or reading it x comma y, that would be 25 comma 0, 20 comma 9.9, 15 comma 14, 10 comma 17.1, 5 comma 19.8, and 0 comma 22.1. 3 asks for the line or curve of best fit. We're going to be doing a lot more best fit lines later, but I can see that this isn't linear, especially because of these 2 points here and here. They really don't follow the trend. This is actually a curve of best fit. My curve is going to look something like this. And when it's not a line, you try and sketch in the best curve that you can. And number 4 wants you to use the graph, use the curve that you just drew. It says, what's the speed of the mass after its vertical distance that it fell is 12.5 meters. So look up 12.5 meters on the x-axis and see what the speed is according to your graph. There's 12.5. See where it hits on the y-axis. And it hits on the y-axis right about there, just above 15. That's looking like maybe about 16 meters per second based on my graph. The official answer key says 15.5, so I would say 16 is close enough. You are allowed wiggle room. The answer is based on the curve that you did. But this is all about plotting, all about curve fitting. This doesn't have a lot to do with actual freefall kinematics and analyzing a freefall kinematics problem. Let's move on to number 5. So 5 all the way through 19 are going to be write down the given information, solve for the unknown, pick your equation based on your givens and unknown. It's following that guess method. Givens, unknown, equation, substitute with units, solve with units. So let's go. Each one of these guys, I'm going to write the givens down, identify my unknown. The trick about a free fall problem is they don't tell you everything. So when you are falling, V initial is 0 meters per second. When you're rising and you're slowing down as you go up, V final is 0 meters per second, and the entire time, slowing down as you rise, speeding up as you fall, the acceleration due to gravity is negative 9.81 or negative 10 meters per second squared. Sometimes if you're on a different planet, it's going to be a different number, in which case they tell you what that number is, or you have to solve for it. All right, number 5. And this worksheet made a liar out of me. Okay, so the first number 5 is not a plug in and solve problem, but we have to know about what happens to acceleration and speed. Well, like I just said, when you're rising or falling, the acceleration is constant. The acceleration is constant at negative 9.81 meters per second, or you can round that to negative 10 meters per second, which means if you drop that rock and you're ignoring air resistance, for every second it gains another 10 meters per second of speed, which is a pretty fast acceleration. Of course, air resistance is a real thing in real life, but if it's a heavy rock, the air resistance doesn't really affect it that much. But this is one point that some people find confusing, and it's the constant acceleration. So like, oh yeah, constant, yeah, it accelerates at constant speed. What? Accelerate at constant speed? Acceleration is changing speed. So if you're accelerating, the speed is changing. So for a freely falling rock, the acceleration is constant, but the speed is increasing as it falls. If you were to throw that rock upwards into the air, the speed would be decreasing. But it's falling, it's on its way down, so the speed is increasing. Again, when we talk about acceleration, your speed increases when the acceleration and the velocity are in the same direction. And if the rock is falling, its velocity is negative or downwards, and it's speeding up, so the acceleration is negative or downwards, which we know to be true because gravity pulls downwards. And I said before that they might ask you to solve for the acceleration due to gravity if you're on a different planet, like number 6. Okay, 2 things. Well, first of all, one thing, but for 2 reasons. D is negative. That 0.72 meters, I'm going to make that negative, and that's for 2 reasons. One, it's to make the math work out correctly in the equation, but also it's correct physics. If you drop something, if you're dropping a rock on a different planet or our planet, I don't care what the planet is, if it's falling downwards, that's a downward displacement. That is going down, that's negative. If you throw something upwards and it rises, that's a positive displacement, but if it falls downwards, it's a negative displacement, and you should write it as such. And again, to be clear, the acceleration is not negative 9.81 because it's not Earth. We're solving for A. And it said falling from rest, so V initial is 0. I know D, I know T, I need A. D is VIT plus 1/2 AT squared. Remember that only the T is squared in that equation. Substitute numbers with units. Anything times 0 is 0, and you wind up with an answer of negative 3.6 meters per second squared. Now, negative is not an answer choice, they're all positive, but it does say magnitude of the acceleration, and we know that magnitude means amount. Magnitude is always positive, that's why the answer is positive. But technically the acceleration is always negative because it always points down towards the surface. I don't care what planet you're on. Number 7 is interesting because they actually have an initial velocity. So many of these problems, the initial velocity is 0 when you are falling. But on this one it says a ball is thrown straight downwards with a speed of 0.5 meters per second. So yeah, we opened this problem with the V initial, and I made that negative because it is throwing it downward. So that 0.5 meters per second is a negative downward initial velocity. So this problem is also a little bit more complicated because they say that the ball is thrown from 4 meters up, like from a height of 4 meters up, but that doesn't necessarily mean that's how far the ball fell, which is kind of like, then why did they tell you that? Which is a good point. You actually don't need to know. Maybe there was a follow-up question relating how far the ball falls to how high the person was when they threw it. I don't know. But if you think about it, it really depends on how long, for how much time was the ball falling. because like, you know, a hundredth of a second after it's thrown, it hasn't gone 4 meters. And, you know, it's like maybe, you know, a 2/10 of a second after it was thrown, it hasn't gone 4 meters. So that 4 meters, that's just where it came from. This might be a good example of a problem that we might want to sketch out. So there's a little sketch to help us visualize what's going on. The sketch isn't really necessary, but sometimes it helps to have a picture. We have a time of 0.7 seconds, and we have an acceleration due to gravity of negative 9.81 meters per second squared. Because even though the ball is thrown downward, as soon as it leaves the person's hand, whether it was dropped or thrown, as soon as it leaves their hand, gravity is the only thing acting on it, and so the ball accelerates towards the ground at negative 9.81 meters per second per second. Now they want to know the speed 0.7 seconds later, so we want to know V final. We know V initial, we know the time. They didn't expressly tell us the acceleration. That's a free fall problem. We have to know the acceleration. That's why I wrote it in blue. It's something that we know, but it's not something they told us directly. We get that VF is negative 7.4 meters per second, which is choice 2. Notice that the choices are positive, but that makes sense because they're actually looking for speed. Speed is the magnitude of velocity, so the negative doesn't actually matter. So 7 is choice 2. For what it's worth, I did a quick d is VIT plus 1/2 AT squared, and I got at negative 2.75 meters. So after 0.7 seconds, the ball hasn't reached the ground yet. If it was thrown from 4 meters, and it's gone only 2.75 meters, it hasn't actually reached the ground yet. So I don't know, that 4 meters, I guess it's just a distractor. We didn't really need it. My picture is also wrong. I'm going to fix that. Technically, I should include the height of the person in that 4 meters, but whatever. Now, number 8 has the moon, so the acceleration due to gravity is not 9.81, it's 1.62. How do I know that? It says it in the problem. So we got an astronaut on the moon, Earth in the background, give him a spacesuit, dropping that hammer from 2 meters up in the air. There is no air on the moon, so at 2 meters high, I should say. Alright, let's continue to read the problem. It gives the acceleration due to gravity on the moon, which is 1.62 meters per second squared. I made that negative because all accelerations due to gravity, I don't care where you are, they are negative because they point downwards towards the surface. The question asks how long will it take, so it wants to know the time. The initial velocity is 0 because it's dropping it from rest. And it says that the hammer is falling to the surface from where it was being held, so that displacement is 2 meters. I made that negative because it's falling downwards, it's displacing downwards. So that's going to matter for the math, but that's also correct physics. So I know A, I know VI is 0 because it's dropping from rest. I know D, and I'm solving for T. Write my formula, sub with units. 0 times anything is 0. Here's another reason why making the displacement negative matters, because when I go to divide through the negative 0.81, I wind up with a positive number for t squared. So can't take the square root of a negative. I mean, you could just make it positive, but this way when you work the numbers out correctly, you don't have to square root both sides. So that 1.6 seconds is choice 3. Next. Falls freely from rest, V initial is 0. It says in the problem that it falls 20 meters to Earth, but I'm not going to write that down just yet, and I'll tell you why in a second. I keep reading. When is the speed of the object 9.8 meters per second? So it's saying that V final is 9.8 meters per second. It's asking about when, so it's asking for the time. The acceleration is due to gravity, so it's negative 9.81 meters per second squared. And number 9 does say that it falls 20 meters, but it's not asking what is the speed at the end of 20 meters after the 20 meter fall. It's asking when is the speed going to be 9.8 meters per second. So really the 20 meters has no relevance for the problem. They're not connecting their question. They're not saying, they're not asking for the time after the object has fallen 20 meters. They're saying what is the time when its V final is 9.8 meters per second. And honestly, I do have enough information to solve the problem. I can do VF is VI plus AT. And when you solve for that time, you wind up with 1 second. Now you have to read the answer choices carefully because choice 1 says, during its entire first second of its fall, the speed was 9.8 meters per second. Choice 2 says, oh, it's 9.8 meters per second at the end of its first second of fall. The answer is going to be choice 2. And while we do get that time is 1 second and that v final is 9.8, it doesn't hold the speed of 9.8 meters per second. It's accelerating as it falls. It's speeding up. And so the speed is changing. It doesn't hold 9.8 for the entire first second. It's only that instantaneous speed at the end of 1 second. In fact, at 0.9 seconds, it was slower. At 1.1 seconds, it's faster. So it's only 9.8 meters per second right at the end of the first second of fall, and so 9 is choice 2. I don't know, I'm starting to think this is going to be another one of those videos I have to break in half. Let's see, number 10. We're given a V initial, and we want to know how high, so we know VI, and we want to know D. Since it's rising, we know V final is 0, and we know the acceleration too, due to gravity. Now we have enough to solve the problem. 44.1 meters, and the answer does come out as positive, which makes sense because it's rising upwards. Next, 11. Now 11 is interesting because it's asking for the total time. Well, the total time is the time that it takes to, it's double the time that it takes to rise or fall, because the time that it takes to rise is the same as the time that it takes to fall, ignoring air resistance. So if you want the total time, you just find the time to rise or the time to fall and double it. So we've got a soccer ball being kicked, and it's not going straight up, but we have the initial vertical velocity. That's really all we need. So V initial is 15 meters per second. Looking for time, two things they don't tell us but that we know. For something rising, VF is 0, and we know the acceleration too because it's free fall. It's the acceleration due to gravity is acting on it. So you can figure out that the time to rise is 1.5 seconds. If it wants the total time to go up and come back down again, double that, you get 3 seconds. Or it's 1.53 seconds, and then if you double it, it's 3.06 seconds. So that's actually wrong sig figs. They gave 2 sig figs on the 15 meters per second. The answer should actually be 3.0 or maybe 3.1. Whatever, it's choice 3. Okay, 12, they give us the mass which we don't actually need. It's falling from rest, so V initial is 0. It's falling 12 meters downwards, we make that negative. The acceleration they don't tell us, we need to know it, negative 9.81 meters per second squared, and they want to know VF. VF squared is VI squared plus 2AD. The answer is not 235.44, don't forget to square root. You get 15.3 meters per second, and I made that negative because it's going downwards. And that lines up with choice 2, 15 meters per second. Got a baseball being dropped, takes 3.1 seconds to fall from the top of a building, wants to know the height of the building, or in other words, what was its displacement. Since it's being dropped, we also know V initial is 0, and the acceleration due to gravity is negative 9.81 meters per second squared. Ball fell 47.1 meters down, so that's the height of the building, choice 3. Dropping a ball wants to know the time when its speed is 20 meters per second. I made that V final as negative because it's falling downwards. 2 seconds, choice 2. Next. In 15, they give us the weight of the object, which we don't need, and we want to know distance. So even though my answer comes out as negative, distance is a scalar, so we just make it positive. 4.9 meters, choice 3. Next. 16 is an interesting question. It talks about somebody jumping straight up into the air, but we're actually going to have to treat this as the basketball player falling from her greatest height. Because things that we know that the time, she was in the air for a total of 0.8 seconds. And we want to know how high did she jump into the air, and that's really all that they tell us. So let's think about how we can look at this problem. First of all, for a free fall problem, we look at rising and falling kind of separately. It's easier to analyze either just the rising or just the falling. And then if you want to look at the whole thing, then you put it together afterwards. So if the total time is 0.8 seconds, that's 0.4 seconds to rise and 0.4 seconds to fall, because it's the same time both ways. So we know the time to rise and the time to fall, and we know the acceleration due to gravity. Now we're looking for how far, looking for d. And there are two formulas that have d in it. Now I know the time, but I don't know VI or VF, so I seem to be stuck. However, I know that when rising, when she jumps up into the air, her V final is 0, and when she's falling from her greatest height back down to the ground, V initial is 0. And to solve for D, I can solve for how high she rises or how far she falls. It's going to be the same number. So if I look at it from the rising perspective, where V final is 0, that sounds promising, except I don't know what V initial is when she's rising. I don't know the speed that she jumps at, so that's not really going to work. But if I look at it from the falling perspective, because it's the same time and same displacement, I do know V initial. I can solve, I do know the time, I do know the acceleration, and now all I need to solve for is the displacement. So let's look at it from a falling perspective and solve for D that way. Make sure to only use the half time, the 0.4 seconds. You get 0.78 meters, and that's choice 2. Number 17, cut and dry. 18, interesting question. You don't have to do any math, they're just asking about the speed at the highest point. When you throw something up into the air, it slows down as it rises, speeds up as it falls, so at the highest point the speed or the velocity is 0. But the acceleration at the highest point is not 0, because it changes direction up there, so the velocity changes. The acceleration is constant due to gravity at negative 9.81 or negative 10 meters per second squared. I'm going to say skip number 19 because it's not actually a free fall problem. The acceleration of 20 meters per second squared is the combination of both the rocket force and the weight. And also, well, rockets don't really have a constant acceleration anyway, but that's besides the point. But this isn't a gravity problem. We're talking about free fall physics under the influence of gravity, and gravity's not playing a role in this problem. I just don't like it. It doesn't fit in with the others. I'm not doing it, so skip it. It's choice 1 in case you're wondering, but skip it. 20 is a good question. It says, if you drop a feather, why doesn't it drop like a stone? Because of air resistance. But that 9.81 meters per second squared is only if there's no air resistance. And air resistance is a real thing on Earth. So it's because of air resistance. If you went to the moon, which has no atmosphere, there's no air resistance. Even in reality, there's no air resistance on the moon because there's no air there. There's no atmosphere at all. If you're looking for a short answer for number 20, the short answer is air resistance. 21 is a bad question. What they didn't say in 21 is that the ball reaches the ground. You dropped it from a 40-meter building, but it doesn't actually say, like, the time of fall, to get to the ground? That's what they're implying, but they didn't actually say that, so that is what they're implying, so let's treat it that way. So dropping from rest, falling 40 meters, how long does it take? It doesn't say dropped from rest, but if you're dropping something, it is from rest, so V initial is 0. Like, numbers like 22 and 21, they may give you the mass or the weight, and you're like, why are they giving that to us? We don't even need it. That's not just like a distractor. There could be follow-up questions later once we talk about mass and force and weight, but for now, we don't need it. I write it down because it is given information, and we shouldn't simply ignore it. There's 23. I made VF negative because it's falling downwards, and so it actually, in terms of the equation, you probably could have left it positive. You wind up with the same answer. And the displacement comes out as negative because it does fall downwards. It's a negative displacement. Choice 3. The moon, so acceleration is not negative 9.81. In fact, it wants you to solve for acceleration. Also, I made that displacement negative because it falls downwards. We wind up with an acceleration of negative 1.6 meters per second squared, which makes sense because the moon's gravity is about 1/6 that of Earth. Choice 1. 3 more. I think we can make the 30-minute mark. Similar to number 24, but this time it is on Earth, so A is negative 9.81. The object, object? displaces 500 meters downward, so I made that negative. I get about 10 seconds, choice 3. Number 26, pretty straightforward, choice 2. 27, it's a dot diagram, and it says for something falling freely near the Earth's surface, well, if it's falling freely, it's accelerating downwards. So yeah, if you drop something, it speeds up as it falls, which means that it's slow to start, and then it gets faster as you go. So when things are slow, the spots are going to be close together because you're not covering as much distance over time. You're going slowly. But then as you speed up, the amount of distance over time that you cover increases. So if you have a fully freeing object, it's going to look like this. 1 second later, and so it's still going somewhat slowly, but then 1 second later after that, faster and faster. The distance per unit time is increasing, it's getting faster. And so the dot spacing is going to grow and grow and grow because the d over t is getting bigger, the speed is getting faster. So in terms of the spacing, it's going to be choice 2. And the other choices, choice 1 shows a constant speed because that dot spacing is steady as it goes. Same d over t, so the speed is constant. Choice 3 actually shows it slowing down because the dots are getting closer together. And choice 4 actually shows like big dot spacing, small dot spacing, big dot spacing. That would be fast, slow, fast. Which is not what I wrote. Let me fix that. Yeah, that actually shows fast, slow, fast. If it was slow, fast, slow, then it would have close dots, spread out dots, close dots. And that's it. So yeah, how about that? I was able to squeeze in all 27 problems within a 30-minute time limit. So stay tuned for the next worksheet. Thanks for listening. And as always, you can email me, HESSEL at rvcschools.org. Email me using your student accounts, please, if you have any questions. Thanks. Bye.